Well, another important introductory topic for our trig is to discuss the idea of an angle being in standard position. So if we're looking at our x and y axis here, we can see that we have an angle in blue. Now, any angle that's in standard position is called standard position if the vertex is at the origin and it opens in a counterclockwise position. So one of the legs, I would say, of the angle is laying here on the x-axis, and the other portion of this angle is going to open up into a counterclockwise motion. Now, we talk about the initial side being the side that's laying on the x-axis. When your angle opens up, or when your angle rotates, the terminal side would be the end, obviously, of the rotation. So we have an initial side, we have a terminal side. We know that this angle is centered at the vertex, or the vertex is centered at the origin. The other thing we need to remember when we talk about trig is we've got to review the quadrants of our Cartesian coordinate plane. So again, our coordinates, or the quadrants, are labeled in a counterclockwise position as well. We know that this first quadrant, we would call that quadrant 1, and the angles in quadrant 1 for theta, we'll call this theta. The angles in quadrant 1 would be any angles between 0 and 90 degrees. Because as soon as we get to the y-axis up here, we know that this value would be 90 degrees, and I should point out that this would be 0 degrees over here. Rotating to the left, we have quadrant 2, and any angles that are in quadrant 2 would be between 90 and 180 degrees. Because we know that we have a straight line here, the x-axis would be a straight line, so therefore this angle measurement over here would be 180. Quadrant 3 would therefore have angles between 180 and down here, which would be 270 degrees. So if my angle were to travel all the way down here and stop, say at that point, we'd be at 270 degrees. And then finally over here in the fourth quadrant, we have angle values that are between 270 and 360 degrees, because if I were to rotate all the way around in a circle and end back here on the x-axis, that is also 360 degrees to go in a complete circle. Now we have special angles. We have quadrantal angles. A quadrantal angle is an angle whose terminal side lies either on the x or the y-axis. So for up here, my quadrantal angles are ones that are on 0, 90, 180, or 270. Okay? So there's 4 quadrantal angles, and they are 0, 90, 180, 270, and I suppose you could consider 360 again as well. Now a coterminal angle is another concept where I can rotate an infinite number of times around the circle. Okay, so an infinite number of revolutions around this in that motion. Now, if I were to start here on the x-axis, rotate 60 degrees, I would end on this blue line. Okay, so if I made that rotation, like it shows, I have 60 degrees. But what if I started again on the x-axis? I rotated all the way around one time plus 60 more degrees. I am still ending on that terminal side, but this time I've rotated 420 degrees. Okay, so a coterminal angle would be an angle whose measure differs by a multiple of 360. In other words, if I only went a portion of the way around, I'm at 60 degrees, but if I went a full revolution plus that small portion, I'd be at 420. So realize that this 420 is really going to be 420 minus 360, or let me write it a different way. 420 is actually going to be the 60 plus 360, and that's where we got the 420. Okay? And I have an infinite number of ways that I can come up with this coterminal angle, right? I have one rotation plus the 60 would give me 420. What if I went 3 rotations plus 60? If I went 3 times around, that'd be 3 rotations at 360 degrees plus the 60 degrees that I know I have to travel in addition, and I would have another angle that would be coterminal to what I'm talking about here. Okay, so that's what coterminal angles are. So we're going to work a series of examples here. Okay, the first example that we're going to work is we're going to find the angle of least possible positive measure coterminal with each angle. And let me back up for just one second and state that when I rotate in a counterclockwise measure, going in this direction right here, I have positive measurements. I have positive angles. If, however, I went this way, which is clockwise, I would end up with a negative angle measurement. So by moving counterclockwise, we have positive values. When I move in the opposite direction, clockwise, I have negative angle measurements. Okay, so looking at this first example here, it's usually helpful to go ahead and draw a picture and see what's happening. I know that I have 908 degrees. So in other words, I'm starting here on the x-axis. I travel all the way around, that's 360. I travel around again, that's 720. I travel around again, and I keep on going, right? I don't really know how many times I'm doing this, but I can figure it out on my calculator. So I know that I'm going to travel a total of 908 degrees, and I'm going to subtract that from what I believe would be 2 times around, because 2 times 360 is 720, because I know those multiples. And if I subtract 908 minus 2 times 360, I get 188 degrees. So in other words, my circle, my angle measurement, continued all the way around to somewhere down here, past 180. And that's how far I traveled. In other words, I went around 2 times plus 188 degrees more to end over here. This value is not only 908 degrees, but it's also 188 degrees. So 908, 188 are coterminal angles of each other. And that was the least positive measure. All right, let's look at one that's negative. Let's look at this one over here. If I have a negative angle, remember I told you that if I move counterclockwise, I'm positive. Well, I'm not moving positive. I have a negative angle. So if I move negative, then I'm going to be somewhere over here in quadrant 4. How do I know that? I know that because to move from the x-axis in this direction, if I were to move from the x-axis over here to the y-axis, that is a difference of 90, right? That is 90 degrees. But my angle is less than 90. It's somewhere at 75. So I know I'm down here in the 4th quadrant. And this is negative 75. But I'm being asked to give back a positive measure that's coterminal with this. So in other words, I want to know what this value is moving in the positive direction. So how would I figure that out? Well, if I know that an entire revolution is 360, I want to subtract off the blue portion. So an entire revolution is 360, but let's subtract off this blue 75 degrees, and I end up with 285 degrees for the red rotation. Okay, so drawing a picture is pretty imperative when we're talking about our trig. It's much easier to draw it out, determine just what quadrant I'm in, based on this, and then kind of go from there. So the next example we want to talk about is a little more obscure. This is kind of how many angles can we come up with in general. If we let n represent just some integer, remember integers are 1, 2, 3, 4, I want to give an expression that generates all angles coterminal with 45 degrees. So let's draw our picture. 45 degrees lays over here somewhere in quadrant 1. So I know that to move that little amount, that's 45 degrees. But what if I moved all the way around 1 revolution plus 45 more? Well, that would be 45 degrees plus 1 revolution times 360. That would end up being 405. Okay, let's do that again. Think again. This time, what if I went 1, 2 revolutions plus 45 degrees? So if I have 45 plus 2 revolutions at 360 degrees, I end up with 765. So I don't know, can you see the pattern forming here? The pattern comes with 45 plus some number n times 360, right? That's going to give me however many revolutions I go around. So in general, the answer to this question looks like, we don't usually write it like that, 45 plus 360n. That is an expression for all angles coterminal with 45 degrees.